Alright, so I just had a power outage, which is fun. Which means I might get disconnected here at some point in the stream. But I don't really care. Still gonna hop on here and I got power back. So I'm gonna be starting on this book, the K&R C book that we have been discussing. I guess I want to see if I have it downloaded on the desktop downloads. What is this guy? No. Let's see. There was a version on... Yeah, let's go ahead and restore since everything crashed. Send this to 2. If I go to Wikipedia K&R C, yeah, this thing. Down at the bottom here, there's a link to 2nd edition, which is the one that I am reading. This one's a little pixelated, but I'm sure it's fine. So I'm on page 16. Let's go and kill that. And let's go and just download this. Make sure that we got it saved off here. And then I'm going to open it instead of in a browser. I'm going to open it over here. There we go. Alright, so let's go, oops. Page 16, the for statement. So a lot of this is going to be really basic stuff. I already started reading, just kind of like couple of minutes before I go to bed each night. And yeah, it's like super basic. So I think my strategy with this is going to be, let's just read it as fast as humanly possible. And if we encounter anything novel that I haven't encountered before, I'm going to highlight it. If there's any exercises that are in the chapters that are interesting, I'll highlight those. And then once I'm done with the book, or once I'm at a point where I want to like take a break from reading, then I will go in and implement some of the exercises. But I'm not going to waste a lot of time on exercises. Like they have one here. Verify the expression get char is not equal to EOF is 0 or 1. It's like, okay, I don't need to do that. I mean, it's something that you would do if you were learning C in the 80s or whatever. Like, I don't need to do that here. Okay, so I have the book loaded up here. This is not the same page as I'm on, so it means that we're gonna have page number differences, unfortunately. Let me actually pull up a version of this book that might be the same page numbers, because I don't like having different page numbers from the book that's on the screen. So give me 1 second, because I had another PDF version here. Yeah, here it is. Let's do... Oh, that's funny. Could have sworn it was in here somewhere. There's no. Okay, I'm just gonna do some searching on the main machine here. Excuse my cough too, because I think I'm coming down with something. Yeah, this looks totally different from the book. So I'm going to just search for K&R C PDF. And I think it was this Color Computer Archive? No. This one maybe? So this one looks more like the book that I have. So let's go down to page 16 and see if it matches. Well, this is 16 in the PDF, not in the book. So this is page 16 here. Yep, this is exactly the way it appears on my book here. So I'm going to download this one. This will be the one that we'll use. And just close out of all this. Open that. And then I'm going to jump over to Cypher 0 Dev and mkdir K&R C. And wait a minute, cd K&R C. Wait a minute. Okay. CP, I'm going to copy from the Linux programming interface, the README there, into here. One thing I didn't do is the Linux programming interface. I had this make file. It finds all the C files and then formats them. So make format, get status. That didn't do anything. Okay, good. Means everything is formatted, or at least it didn't find anything that wasn't formatted. Okay, let's go in and vim the README here. The Linux, the C programming language. And this is Brian W. Kerningham. I always pronounce it Kerningham, but it reads Kerninghan. And Dennis M. Ritchie. Okay. On reading K&R C. Same deal. So we'll just start with chapter 1. And let's get the index here. This will be a tutorial introduction. And how many chapters we got? 8 chapters and 3 appendices. 1, 2, 3, 4, 5, 6, 7, 8, and 3. Okay. Let's do. Oops. Okay, tutorial introduction. Types, operators and expressions, control flow, functions, and program structure. Pointers and arrays, structures, input and output. Finally, the Unix system interface. A is a reference manual. B is standard library. C is summary of changes. Okay, looks good to me. Oops. Git init. Excuse me. Cool. Might as well create the repo on GitHub. Why not? Oops. Not what I wanted. Thank you. Here. New repository. Call it K&R C. Public. Create repository. And then here, I'll do this. What? How did I copy that escape sequence? What the hell? There we go. And then we say git push upstream origin main master. Let me add that. Okay. Fresh over here. Look at that. All right. You're all set to start reading. So I already read the preface and the introduction. There's I think there are two prefaces. The preface for the second edition and a preface. So I already read all this. And I got to page 16. Basically just going through like very basic aspects of the language. Printf, hello world. This is a Fahrenheit calculator. Converts Fahrenheit to Celsius. He does it with a while loop, and then he does it with a for loop. I guess he's still doing it. Oh, no, he explains the difference between integer division and floating point division. Does some different printf format specifiers. And this is where we're skipping exercises. So the exercises up here. Run the Hello World program on your system. Experiment with leaving out parts of the program to see what error message you get. Experiment to find out what happens if printf's argument string contains /c, where c is a character. Okay. Don't care about those. These ones, modify the temperature conversion program to print a heading above the table. Do not care. It's just a simple printf above the loop. Write a program to print the corresponding Celsius to Fahrenheit table. Again, it's just inverting the conversion. Not really that challenging. Not something I'll waste time for. All right, so now we are on the for statement. So you converted the Fahrenheit to Celsius calculator to a for loop instead of a while. Symbolic constants. How to do a pound define. So you pound define all this stuff up here, so you don't have to specify magic numbers. Character input and output. You can call get car and put car. And then that leads us to page 16. File copying. So this is where I left off last night before I went to sleep. Let's go ahead and speed read. Given get car and put car, you can write a surprising amount of useful code without knowing anything more about input and output. The simplest example is a program that copies its input to its output one character at a time. So you read a character while a character is not in the file indicator, output the line the character just read, and then read a character again. So yeah, pretty basic loop here. Converting a C gives us a main. We do get char, exactly what we want. The relational operator not equals means not equal to. What appears to be a character on the keyboard or screen is, of course, like everything else, stored internally just as bit pattern. The type char is specifically meant for storing such character data, but any integer type can't be used. We use int for a subtle but important reason. So probably because of the EOF comparison. The problem is distinguishing the end of the input from val data. The solution is that getChar returns a distinctive value when there is no more input, a value that cannot be confused with any real character. This value is called EOF, or end of file. We must declare C to be a type big enough to hold any value that getChar returns. So he's just doing pound include on standard IO. So let's do make dir chapter 01, cd into there, vim test EOF definition C, main pound include standard io.h, and then in here we're just gonna say printf %d, why not, new line, and we'll give it EOF. And we need a standard lib for the exit status. We don't need it, but it's there, so we'll use it. So EOF is defined as -1. -1. I guess you can strip those, doesn't matter. And if we do vim makefile, oops. You know what? I'm gonna go back over to our K&R, or sorry, Linux programming interface, and then do a find makefile cp chapter 63 slash makefile into K&R C, so sorry, just one, K&R C chapter 1. This guy, don't need any of this, so go and zig can go away, thank you. We don't need the ref stuff, it just program binaries. Yep. We don't need that. We don't need these, obviously. And then we don't need these. Okay. So we just say make, build, yep, -1. Cool. So EOF is defined as -1. If you have a char, that means that the bit pattern is a bit weird. Huh. That is super weird because, like, I guess this is why ASCII is 7-bit instead of 8-bit. Because that most significant bit is going to be your sign bit. And basically negative values were considered, signaling. So -1 is EOF. So if you look at if you do Python and we look at the binary representation of -1, well, that's not helpful. I want the 2's complement. So let's just go here, say 2's complement calculator. And we give it 8-bit The decimal value -1. So the 2's complement would be all 1s. And that would be the maximum value. So that'd be 255, I believe. Python, if I say ordinal of this, and then say, I think I can do it like that right now. Sorry. It's like this. 0, and then I give it B. Yeah, 255. So that means if we look at an ASCII table, 255 should be EOF. Obviously this is ASCII, so it's we'll do an 8-bit ASCII table, even though it's not ASCII. All the way down at the bottom. Here's all 1s. It says extended ASCII code. And if we look at all 1s, it should be EOF control signal. It's not. It's just Y. So, if we have that bit pattern, vim test EOF, let's just do the same program, why not? It's kind of related. So let's just say C for character. Can I do that? Let's see. C format string to output a integer as a single char. Yeah, C. What about a format string to output the binary representation of the integer? No format. Oops. Print binary, and we'll say, hey, you're going to be EOF, and put char new line. Oh, we need to make it a char, not a string. Okay. Yeah, what is char bit? What the hell is that? Limits. Wait a minute. That seems suspicious. Oh, because an integer is on this architecture has, I guess, 32 bits. This looks like about 32. Python len of this. Yeah, it looks like 32. Integer has 32. So that means when we get char, there must be a process that converts the character to an integer. For almost every character, it's just going to be that the lower precision bits are set up to 7 bits, or 8 bits for that matter. Yeah, all the way up to 8 bits. And then the higher order bits will be set to 0. Okay. That works. But I'm kind of curious why I can't print this as a character. Maybe if I need to cast the EOF down to a character. Oops, sorry. Make, build. Still doesn't come out as a character. And that's an unsigned int. Okay. What is charbit here? I don't know what that is. If I did like a -2 here, it's set as 0 on the right hand side, I think. Sorry, I need to build it. Yeah. Huh. If I change this to a char, oops, that should give me 8 bits, right? Yeah. So why can't I print out? Is that not a valid Unicode code point? UTF-8. Encoding tester. So this would be FF. Yeah, it has a code point. Oh, but you have to have these 00 prefix on it. So if I did, instead of C, if I did %C here, and then I gave it 0 EOF, maybe because it doesn't encode to UTF-8 like that. Yeah. It should be this here. Yeah. Okay. That makes sense. Okay. So I just wanted to play with that a little bit to understand, like, why is it that they use int? Because like most languages, a byte or a char is like an unsigned 8-bit integer, but an integer in C is a signed arbitrary length, like architecture specific length integer. And we saw In the case of my computer, the int was 32 bits long. So it is kind of weird that they do that. So the problem is distinguishing the end of the input from valid data. The solution is that getChar returns a distinctive value when there is no more input, a value that cannot be confused with any real character. This value is called EOF, or end of file. We must declare C to be of type big enough to hold any value that getChar returns. We can't use char because C must be big enough to hold EOF in addition to any possible character. Therefore, we use integer. EOF is an integer defined in standard io.h, but the specific numeral value doesn't matter as long as it is not the same as any char value. By using the symbolic constant, we are assuring that nothing in the program depends on the specific numeric value. The program for copying would be written more concisely by experienced C programmers, and C any assignment such as C getChar is an expression has a value, which is the value of the left-hand side after the assignment. This means that the assignment can appear as part of a large expression. If the assignment of a getChar to C is put inside the test part of the while loop, the copy program will be written in this way. Yeah, I was going to say, you don't need to do the assignment twice like that. The while gets a character, assigns it to C, and tests whether the character was the end of file signal. If it was not, the body of the while is executed, printing the character. The while then repeats. When the end of the input is finally reached, the while terminates, and so does main. This version centralizes the input. There is now only one reference to getChar and shrinks the program. The resulting program is more compact, and once the idiom is mastered, easier to read. You'll see this style often. It's possible to get carried away. Am I on the right page here? Yeah, it's possible to get carried away and create an impenetrable code. However, a tendency that we will try to curb. The parentheses around the assignment within the condition are necessary. The precedence of not equals is higher than that of equals, which means that in the absence of a parentheses, the relational test not equal would be done before the assignment. So the statement getChar is not equal to EOF is equivalent to getChar is not equal to EOF assigned into C versus getChar assigned into C is not equal to EOF. Yeah. This has the undesired effect of setting C to 0 or 1, depending on whether or not the call to getChar encountered an end of file. More on this in Chapter 2. Exercise 1.6, verify that the expression getChar is not equal to EOF is 0 or 1. I don't care about doing that. Write a program to print the value of EOF. Oh, I did that. Character counting. The next program counts its characters and is similar to the copy program. Can I just use like that and then maybe go like that? Let's see, character counting. That is not big enough. So we need to zoom out a little bit. There you go. Alright, so we got our pound include, standard io.h. Count characters and input, first version. So we go main. We got our long count, assigned to 0. And we say, well, EOF, then we do a plus plus NC instead of NC plus plus. And they print out as a long. The statement plus plus NC presents a new operator. I'll be right back. I need to get something to scratch my back. All right. Let's see. The statement plus plus NC presents a new operator plus plus, which means increment by 1. You could instead write NC is equal to NC plus 1, but plus plus NC is more concise and often more efficient. There is a corresponding operator minus minus to increment by 1. The operators plus plus and minus minus can be either prefix operators or postfix. These two forms have different values in expressions, as will be shown in chapter 2, but plus plus NC and NC plus plus both increment NC. For the moment, we will stick to the prefix form. Prefix means that it increments and then the expression is evaluated to the new value, whereas postfix, the expression is evaluated to the old value. I believe that's the way it works. The character counting program accumulates its count in a long variable instead of an int. Long integers are at least 32 bits, although some machines int and long are the same size. On others, int is 16 bits. Kind of curious what all the sizes are on my machine. Vim test int sizes.c main okay. Sorry. Pound include standard lib.h. Don't know why that's not even included by default by the macro. Okay. So in here we can say printf. Actually, there was a file here, or a function here that I had in this test EOF file, but that was like print binary of char, which isn't really great. So what I'm going to do is just say like printf size of int is equal to percent %d, and then this will be size of int, like that. And I need standard IO, and format specifies int, but the argument has type unsigned long. So size of, I guess, gives back a unsigned long. I think I just do LD like that. Yeah. Okay. And I want to do like a macro here. Print size. And then this is going to be printf of %s. No. I forget how to do this. But it's definitely going to be size of I'll leave it like that. Size of new line. Percent LD. char int long unsigned long int unsigned int. Let's see, what are all the primitive types in C? Yeah, let's try it. Void. Oh, there's signed and unsigned char. Short. It's another one. A long, yeah. I think that should be 128, right? Test int sizes. So all the characters, void is a single character, all the characters are a single character, obviously. Short is 2 bytes, which will give you 2 to the power of 16. And then 2 to the power of 16, is that like 6,500 something? What is that? I forget. Oops. Please go away, thank you. 2 to the power of 16. Yeah, 65,000. And then we got our 32-bit values, which are integers. We got our longs and our longs, which are both 8-bit. But if I compile this for 32-bit, yeah, it doesn't make sense to do the signed version because everything's signed by default, right? So I'll just take those out. We'll say bool here. Should just be 1 byte for each. And then we got our floating point types, which are float, double, and long double. I haven't heard of that one. Printf. Oops. Forgot to put semicolons on those. Alright, let's fix these guys up. Void in floats for 16. Okay, 16. Long double actually does get to 64 bits. I think it's mainly. Wait a minute. 8 bits. 8 bytes is 64 bits because it's 8 times 8. So size of long double is a 128 bit because 2 to the power of 16 is 128. That's not. Sorry, 16 times 8. 2 to the power of, I don't want a brain fart there, 16 times 8. There we go. It's the maximum value. I just want 16 times 8. It's 128. There we go. I don't know why my brain farted there. Oh, it's complex types. I forgot about those. I'll just put some spacing here for ease of reading. Oops. So we got to include complex.h. Yeah, I didn't think these are built into the language. They're more of a library. Complex. And then here would be a long double complex. Float, double. So I imagine these are gonna be twice as big. Yeah, that makes sense. Because there is the real and imaginary parts. So complex basically just doubles the size of the floats. I want to see what this thing. How do I see the C code post the pre-processing step, but before compilation? I think you say -e. Okay. GCC-E. And we just give it a test int sizes. Okay, this will expand everything out. I was thinking maybe complex would get expanded out too, but I guess it's not a preprocessor thing. Oh, look at all this fun stuff up here. Whee! Cool. All right. Enumerations I don't care about. Let's ask AI. How do I compile for x86 32-bit on a 64-bit machine? I guess this would have a dependency on test inSizes.c. And we can use GCC, that's fine. And then this would be our $caret. This. Make expanded. Make missing separator 17. this like a white space thing? Fucking hate makefile sometimes. Makefile. Yeah, it looks like it's a white space issue. Good job, guys. Okay, we'll do that. Do that. Do that. Do that. Do that. Do that. There we go. Make expanded. There we go. And then the other thing I wanted to do was build test int sizes 32, which we will have to use this. Fucking ChatGPT never copies. Alright, we want to do -g -o0. Oh, we don't need this reflib shit either. M32. This will be our target $@. Oh no, sorry. $@, $caret. Okay. GNU stubs 32, no such file or directory. Doesn't work. Okay. Sudo pacman s lib32 glibc gcc multi-lib. Hey. Oops. Boom, boom, boom. Okay. So this will be our $@, $caret. Get rid of this guy. And then we'll keep the G00. Hey, look at that. So naturally, the Size of fold is still 1. The characters are still 1. The short is still 2. The unsigned int, or the integers are 4. Here's where the long was a 4 byte value, whereas the long on 64-bit is 64 bits. So this long is 32. You have to get the unsigned the long here. I'm not gonna do the signed versus not signed because it's just kind of confusing, the whole thing. Because unsigned and signed have the same widths, so they're just confusing everything here. There we go. And put bool up here. Okay, that looks good. Make clear. Make. All right, build int sizes 32. Okay. So we got 1, 1, 1, 2. So everything's the same up to integer, or sorry, up to long. So an integer on 64-bit or 32 is 4. As soon as you go to long says, okay, long's going to be 64-bit, and a long will also be 64-bit. Whereas in 32-bit architecture, a long is only 32-bit. So basically, long matches whatever architecture size you're on, whereas an integer is always 32 bits. And a long is supposed to be is always 128 bits. No, always 64 bits. Sorry, or always 64 bits. So only one that's different here, like if I do an output of this, so I do this to temp 64. I do this to temp 32, and a delta between temp 32 and 64. So it's the long is the only thing that's different on the normal integers. The long double, so it's always the long. The long is where there's issues. Whether it's a long double complex, or just a regular long. I think I do it like this. And I can run it like that too. Oops. There we go. That's a fun little exercise. So you got all the different types, sizes, outputted, and computed the deltas between the two architectures, and we cross-compiled with ZigCC. I tried doing it with GCC, but it's notoriously frustrating. All right. I forget where we left off. The character counting program accumulates its count in a long variable instead of an int. The long integers are at least 32 bits. Long, yeah, it's 32 bits on a 32-bit 64 on a 64-bit system. Although on some machines, int and long are the same size. Yep, like on 32-bit. On others, int is 16 bits. Okay. With a maximum value of 32,767, and it would take relatively little input to overflow an int counter. The conversion specification LD tells printf that the corresponding argument is a long integer. It may be possible to cope with even bigger numbers by using a double precision float. We will also use a for statement instead of a while to illustrate another way of writing a loop. So we go into our main and we just use a float. And we use the for to do the initialization. And increment. Basically consolidating that to single line. It is funny that the style is here to put the semicolon on a separate line. Not my preference, but it is interesting they did that. Printf uses %f for both float and double. %.0f suppresses printing of the decimal point in the fractional part, which is 0. The body of the for loop is empty because all the work is done in the test and increment parts. But the grammatical rules of C require that for statement have a body. The isolated semicolon, called a null statement, is there to satisfy that requirement. I don't think you need that. Let's test that out. Vim count.c pound include standard io.h main standard lib. And here we're gonna say double nc for nc is equal to 0. And here you can do it all in one, like double. We'll do an int here. I don't want to do a double. Int 0 get char is not equal to EOF. And then we say plus plus nc. I think you put the semicolon here. Printf %d new line. There you go. And we need to put nc here. Interesting, it does put it on new line there. Emacs. Save and close. Thank you. Can you please close yourself? Quit. Control X, Control C. Okay. K&R C. And then RM. Emacs. Let's try this again. Count.c. We go over here. We're just gonna backspace our way to success. File, save. file, quit. There we go. Cat count. Make. Build. Count. Echo foobar into build count 7. Huh. I wonder why running it alone you never get EOF. It's just blocked reading because its standard input's never closed. That's why. Standard input is the terminal's input. So what I could do is say Control D here, and it'll give me 0. Or I could say hello. So that's how you do it there. Okay. I just wanted to test that out. I mean, the semicolon on the new line, I guess, is a style thing. And would that be, that wouldn't be valid because it's not declared. Oh, interesting. Interesting. How did that work? Oh, okay. There we go. Sorry. Okay. Alrighty. Make clean. RM count. Nothing. Don't need that. And then vim.get. Okay. Cool. Alright, let's continue onwards. Printf uses %f for float and double, %0. Okay, I already read that. The null statement. So we were talking about the null statement. Satisfy that requirement. So in bash, there's a similar null statement, which is colon. We put it on a separate line to make it visible. Before we leave the character counting program, observe that if the input contains no characters, the while if for test fails on the very first call to get car and the program produces 0, the right answer. This is important. One of the nice things about while and for is that I'm gonna get this light going on here because my eyes are not. There we go. One of the nice things about while, this is rather, there we go, that's a little better. One of the nice things about while and for is that they test at the top of the loop before proceeding with the body. If there's nothing to do, nothing is done, even if that means never going through the body loop. Programs should act intelligently when given 0 length input. The while and for statements help ensure that programs do reasonable things with boundary conditions. Line counting. The next program counts input lines. As we mentioned above, the standard library ensures that an input text stream appears as a sequence of lines, each terminated by a new line. Hence, counting lines is just counting new lines. So we just declare an integer for counting and one integer for new line. We set new line to 0, and then we get our car. And if car is equal to new line, then we increment new line. print out then. The body of the while now consists of an if, which in control turns increment. The body of the while now consists of an if, which in turn controls the increment plus NL. The if statement tests the parenthesized condition, and if the condition is true, executes a statement or group of statements and braces. That follows. We have an again indented to show what is controlled by what. The double equal sign is the C notation for is equals to, like Pascal single equals or Fortran's dot eq dot. I'm not familiar with Fortran. This symbol is used to distinguish the equality test from a single equal that C uses for assignment. A word of caution, newcomers to C occasionally write equals when they mean double equals. As we will see in chapter 2, the result is usually a legal expression, so you will get no warning. A character written between single quotes represents an integer value equal to the numerical value of the character in the machine's character set. This is called a character constant, although it's just another way to write a small integer. So for example, wait a minute, a small integer? Small as in like relatively small, or small as in like the integer size small? That's a short, not a small. Okay. So for example, A is a character constant. In the ASCII character set, its value is 65. The internal representation of the character A, of course, A is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. The escape sequences used in string constants are also legal in character literals, constants. So /n stands for the value of the new line character, which is 10 in ASCII. You should note carefully that new line is a single character, and in expressions, it's just an integer. On the other hand, quote n is a string constant that happens to contain only one character. Well, it also has the null terminating character, byte, at the end. The topic of strings versus characters is discussed further in chapter 2. Write a program that counts blanks, tabs, and new lines. Nope. Write a program to copy its input to its output, replacing each string of one or more blanks by a single blank. Write a program to copy its input to its output, replacing each tab, each backspace, and each backslash by // This makes tabs and backspace visible in an unambiguous way. I'm not doing that. Word counting. The fourth in our series of useful programs counts lines, words, and characters. It's literally a command for that already. With the loose definition that a word is any sequence of characters that does not contain a blank, tab, or new line. This is a bare bones version of the Unix program WC. Exactly. Okay, so we pound define in and out, inside a word, outside a word. So it's like a state machine type thing. So count lines, words, and characters and input. So we have our character, our new line count, our word counts. So this is number of lines, numbers of words, and number of characters. Temporary storage for the character, and then the state that we're in for the state machine. So we start as outside a word. Okay, we initialize all of our counters to 0. Then we enter in the while loop, getting a character each time until we EOF. We increment our character count, because as soon as we get a character, we can increment that. If the character is a new line, we increment a new line count. If the character is equal to a space or a new line or any white space, then we transition to the out. If a state is, if we aren't on a white space, if we're on a non-white space character, if our state is equal to out, then we transition to in. And we increment our word count. So this is at the start of the word we increment our word count, not the end. And at the end, we just print out all of our characters. So it's a leading edge detection of a word, not a trailing edge detection. Every time the program encounters the first character of a word, it counts one more word. The variable state records whether the program is currently in a word or not. Initially, it is not in a word, which is assigned the value out. We prefer the symbolic constants in and out to literal values 1 and 0 because they make the program more readable. In a program as tiny as this, it makes a little difference, but in larger programs, the increase in clarity is well worth the modest extra effort to write it in this way from the beginning. You'll also find that it's easier to make extensive changes in programs where magic numbers appear only as symbolic constants. The line so-and-so is equal to 0 sets all variables to 0. This is not a special case, but a consequence of the fact that an assignment is an expression with the value and assignments associated from the right to left. It's as if we had written the parenthesized version of it. The operator or means or, logical or. So the line so-and-so says C is a blank line, or C is a new line, or C is a tab. Call that the escape sequence. /T is a visible representation of the tab character. There's a corresponding operator and. For and, its precedence is just higher than or. Expressions connected by and or are evaluated left to right. And it is guaranteed that the evaluation will stop as soon as the truth or falsehood is known. I think or has higher precedence, right? There is a corresponding operator and for and. Its precedence is just higher than or. Oh, that's right. Or is the lower in precedence. That's right. If C is blank, there's no need to test whether the new line or tab, so these tests are not made. This is a particular point here, but is significant in more complicated situations, as we'll see soon see. The example also shows an else, which specifies an alternative action if condition part of the if statement is false. The general form is if expression statement, else statement too. One and only one of the two statements associated with an if else is performed. If an expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can be a single statement or several embraces. In the word count program, the one after else is an if that controls two statements embraces. Exercise 111. How would you test the word count program? What kind of input? It was like it to cover bugs. I don't care about that. Write a program that prints its input one word per line. Don't care about that. Arrays. Yeah, my goal is to get through this tutorial as fast as possible. We're not going to do any of the exercises unless they are really interesting or things that I don't know. All right. Let's write a program to count the number of occurrences of each digit of whitespace characters, blank, tab, new line, and all the other characters. This is artificial, but it permits us to illustrate several aspects of the C program. This reminds me, like all this stuff we're doing using these APIs like get car and put car, which ultimately resolve into reads and writes syscalls. But a better way to implement these is just to create a generic algorithm that operates on memory, blocks of memory, and then memory map your files into your memory and just pass a point into the algorithm. Instead of having like an algorithm that's for files and an algorithm that's for, arbitrary memory. All right. Let me reread this because I wasn't paying attention. Arrays. Let us write a program to count the number of occurrences of each digit of whitespace characters and all other characters. This is artificial, but it permits us to illustrate several aspects of C in one program. There are 12 categories of input. So it's convenient to use an array to hold the number of occurrences of each digit rather than 10 individual variables. Here's one version of the program. So we got our digit array, we got white space, and we got other. And we got a character buffer, temporary buffer for a character. And then we got I as an increment, integer. We initially initialize all of our digits to 0 because they don't have the initialization syntax in this version of C. And then we go in a while, we get car. We increment C minus the literal character 0. I've seen this trick before. This is a neat trick. If you want to get the numeric representation of a digit character, you subtract 0 character from it, which makes total sense. And then we print everything out. The output of this program on itself is digits 93001. White space other. The declaration n digits declares n digit to be an array of 10 integers. Array subscript always starts at 0 in C. So the elements of n digit 0 to 9. This is reflected in the for loops that initialize and print the array. Subscript can be any integer expression, which includes integer variables like I and integer constants. This particular program relies on the properties of the character representation of the digits. For example, the test, oops, what the fuck? Let's go back here. I don't like this. Can I do this? This. Maybe if I make it smaller. There was like a, I don't like this. Oh, you can do dual? That's not right. Night mode? What? I kind of like that. I might leave it in night mode. All right. For some reason, it's not giving me a tree here. Probably because there's no index. Let's go home. And then we'll do hold down right. There we go. Let's go to page 23. So it's trying to do. Too far. There we go. All right, so for example, the test, if C is greater than or equal to 0, and C is less than or equal to 9, determines whether the character C is a digit. If it is, the numeric value of the digit is C minus is character 0. This works only if 0, 1, 9 have consecutive increasing values. Fortunately, this is true for all character sets. By definition, chars are just small integers. So char variable constants are identical to ints in arithmetic expressions. This is natural and convenient. For example, C minus 0 is an integer expression with a value between 0 and 9, corresponding to the character 0, 9, stored in C, and is thus a valid subscript for the array n digit. The decision as to whether a character is a digit, white space, or something else is made with the sequence pattern condition statement, so-and-so. Occurs frequently in programs as a way to express multi-way decision. The conditions are evaluated in order from top until the condition is satisfied at the bottom. Until some condition is satisfied. At that point, the corresponding statement part is executed and the entire condition construction is finished. Any statement can be several statements enclosed in braces. If none of the conditions is satisfied, the statement after the final else is executed if it is present. If the final else and statement are omitted, as in the word count program, no action takes place. There could be any number of else if statement condition statements. Groups between the if and the final else. As a matter of style, it is advisable to format this construction as we have shown. If each if were indented past the previous else, the long sequence of decisions would march off the right side of the page. Switch statement, to be discussed in Chapter 3, provides another way to write a multi-way branch that is particularly suitable when the condition is whether some integer or character expression matches one of a set of constants. For contrast, we will present a switched version of this program in section 3.4. Exercise 113, write a program to print a histogram of the lengths of words in its input. It's easy to draw the histogram with the bars horizontal. A vertical orientation is much more challenging. Write a program to print a histogram of the frequencies of different characters in its input. This one actually interests me because histograms are used so often in the BPF stuff. So write a program to print a histogram of the length of words and the frequency of different characters. Oh, okay. Them. So histogram, if I bring up just like a scala draw here, histogram has the form of there's buckets, and then each bucket has a value. So that would be a histogram. So these are the different buckets. And then the length of the bar is the value. So this is why he's saying that printing it horizontally is simple. When you want to print the buckets going up like this, it's a little bit harder. Mainly because like line wise you have an infinite amount of lines in your output and a bounded size of columns, but like I guess it doesn't matter. We can just wrap. It's not too hard. But our data structure here, let's think about our data structure. It's going to be an array. Each array has values. So horizontal histogram will take in a char star, or what should this thing be? A long star called array and a size t just called len, and it's going to return void. We'll call it print histogram, horizontal histogram. So this one's easy. We just say, hey, for int I is equal to 0, I is less than len, plus plus I. So that'll visit every element of the array. Need to fix up my length here. Okay, then in here, let's see, the two programs here are the lengths of words and the frequencies of different characters. So the length of words probably not going to get too big, but the frequencies of different characters could get, you know, on a significant data set could get really big. Ideally what you do is like find the maximum and scale that to be your 100%. So that'd be scanning over each one of these. Sorry, messed up the thing there. So we're going to have to declare a long, call it max. We'll set it equal to 0. And then we say if our r sub I is greater than max, then now max is equal to r sub I. So now we have our max value. So now we can scale everything appropriately to that. So how many columns do we want? Well, we'll pound define that up here. We'll say calls is going to be maybe we'll say 100. So we have our max value equal to 100. It's a long, which is an integer type. If we divide it by itself, or if we divide that by 100, how do we want to do this? So we have 100 calls, and say we have a value which is like 250 is our max value, and we want 250. So we say 250 is to 100, as is x is to y, and they have to solve for y. So we cross multiply, we say 250 y is equal to 100x. Sorry, is equal to 100x. And we're trying to solve for y, so then we have to divide both sides by 250. And that'll give us y as a parameter of x. So in here, so this is going to be obviously calls times our value divided by our max. That'll be our equation here. So at 250, you would have 100. At 25 divided by 250 would be 1/10. Be 10, yeah, okay. So everything would be proportional that way. All right, so now we're going to have to visit it again, because we need to calculate the max initially. And then we'll say printf out our value, which is going to be r sub I. And we'll do I here, which will be %d. And then this would be a %s here. I'm going to need a new line. This will be I. This will be a repeat of the character I guess I should say the character of this, repeat that n number of times, which will be that number of times, and that'll be our entire program there. So this is going to need pound define standard io.h. Oops. Sorry, pound include. I don't know why I did define. Okay. Then we need to define this repeat function, which is a char star is the return, repeat, takes in a char r and a n integer. And the problem with this is that we also need to pass in a buffer. Or you can just do the heap allocation. That'd be really sloppy though. Is there a built-in way to do this in C? In C, how do you repeat a char in a format string n times where n is determined at runtime? I don't think there's a built-in way. Oh, we could just do that. Just write it out instead of allocating it up front and doing printf. That makes a lot more sense. So let's do that. Printf, we'll give it a new line here. And then I'm going to take away this repeat. I'll just do it in line. Avoids that allocation. And then I'll grab all of that, put that down here for now. This will be fine. Okay, so here we're going to say for j, int j is equal to 0. J is less than this expression. And then plus plus j. And then for each one of these, we're going to say printf the character. Or you can say put char. I think put char is a little bit more simple here. We'll do a hash character. We'll do the same thing here. Put char. And then we can delete that. Okay. So that's the horizontal histogram. The vertical I'm going to implement, but I want to test the horizontal one out first. I can't assert. We'll do it like this. Pound include assert.h and standard bool. All right. Main. We'll pull these up, why not? So we'll need standard lib here. Here we're going to say for we'll just do a fake thing here. we'll just say int, or sorry, it's a long R, we'll say 10 here, and then I think I can do like this now. 0, 1, 2, 4, 8, 4, 2, 1, 0. I think I need to put commas here. In fact, I know it. There we go. And then here we can say print horizontal histogram, and we'll give it the R and size of R. Make build, this will be, I just called it histogram.c. Okay. Make build histogram. That's wrong. Where did I go wrong here? Print f out array length is len. If we look up here, it's 80. That seems wrong. Should be 8. Why is that? Oh, it should be 10, sorry. Well, we'll bring it down to 8. And we'll drop, oh, we'll say 9. There we go. $72. So 72 divided by 9 is 8. There's something about, so 8 is how many bytes are per long. So the size of array is how many bytes are there, not how many elements. What is, how do you get how many elements are in an array in C? Oh, you have to divide it by, yeah, I remember seeing that syntax. Divided by the size of the array element. I think that's how you do it. All right. Let's make it, build it. Hey, look at that. Got a nice histogram. So let's do the vertical version of it. Print vertical histogram. So when we're outputting it like this, we could paint into a buffer then display the buffer. That's one way of doing it. I think the easiest way to do it would be to allocate a buffer of characters, a two-dimensional buffer of characters, and then just iterate over it and fill it in. And then display that buffer. The problem is that like the horizontal one, I wasn't bounded by how many elements of the array, and the vertical one, I also don't want to be bounded, which means that we can't really pre-allocate up a two-dimensional buffer. Can't pre-allocate it, but we could potentially. We still need to know the maximum value, so this is something we need to compute to know how tall it should be. And we're saying vertical rows is going to be 100. Let me just replace this here. Okay. I guess we could pre-allocate the array, the buffer, because you know how many elements are in the source array. And we know the height is going to be vertical rows. So let's go ahead and do that. So we'll say like output is going to be char array that I like doing XY like this. So the Y is going to be the len, and the X is going to be vertical rows. And then we're going to have to add some offset for the index, and actually we can't print the index. We can print the last digit of the index, but we can't print the index itself. But let's go ahead and add that in here. Okay, and then we'll initialize everything to be the space character. We'll do X, why not? What is vertical rows plus 2? What is that like? That's a constant. Variable? Oh, because, wait a minute. Well, fuck it. Let's just initialize it here. For int I is equal to 0, I is less than vertical rows plus 2, I, or plus I, and then we do the same thing for j, but j is going to be length, j plus plus, and here we say output sub I sub j is equal to, we'll just give it the character x. And then I'm just going to comment this out here because that's not helpful right now. Then here we're going to have to print out the matrices. And here we're going to go row column. Okay, so this will just be print or put char, and we do output sub I sub j, and at the end of the line, so this would be at the end of the line here, we gotta put char a new line, and then at the end of all of it we need to put char a new line, and then finally so we don't need this plus 2 then, because we can just output that after the fact. Yeah. Okay. So once this is done, it means a new line is done. Once this is done, that means that all of the rows and columns are done. So we need to then iterate over it again. But this time we're going to iterate over this. And we'll change this to I, just to get our nesting right. And here we'll say printf, we'll just say %d and give it I and have it to do here. And we'll do this mod 10. So go to 0 up to 9 and then wrap around. And at the end here we'll do another new line. Alright. Let's try doing that. So print vertical histogram. I don't have the actual filling of the characters out yet, but at least it'll get us. Okay. But we have 100 height, and we don't want 100 height. We want maybe like vertical rows to be like what, like 20 at most. There we go. Yep, that's exactly what we wanted. So now we got to fill in our shit. Change that to be a space. And basically we're going to iterate over all the elements of the array. So right now we're going to be iterating over elements of the array. We're going to get the y values. So I'm actually going to call this y to not get confused here. And then this will compute how many we get our value, we divide it by the maximum value, and then times it by vertical rows to get our x. But we're going to be going from the bottom up. So this needs to be minus minus. This x needs to be vertical rows. So we start at vertical rows while x is greater than. So x starts at 100. So our buffer goes, it's addressed in inverted from the actual counting. So we have to say we're going to be at the vertical row, which is at the bottom. And then while x is greater than this value that we've computed, actually, what we'll do is we'll pull this out. Say if, and then we'll put braces around this because it's going to be a multi-statement thing. We don't need put chars. We don't need that either. Okay. If else. There we go. I is equal to while x is greater than 0, greater than or equal to 0, minus 1 here, because we're at vertical rows, but minus 1 because it's offset, greater than or equal to 0, then if x is greater than this value that we computed here, then output sub I sub x sub y is going to be equal to, so let me put boop boop, and then we'll just do what, like that. Okay, so we're going from vertical rows minus 1, and we're saying while it's greater than or equal to 0, so any valid indice in this array, we're just going to decrement up to that number. And if it's greater than the value, vertical, which is the, I need to have a good name for this expression, but it's the normalized value. So say it was at 100 and we have or say it's 20. So and 20 is the max. So we got 1, we get the value 20. So while x is less than the value 20, so if I did a less than here, that would print the histogram. And let's go ahead and do it. I know it's what it's going to do. It's going to print the histogram upside down. Yeah, so it prints it upside down. Now, if I just change this to be a greater than, I'm pretty sure that's not going to fix it. Yeah, it inverts the coloring. So what we need to do is actually invert the indices. Okay, so we need to take this value, we need to flip it, basically. So we could flip it on its to a negative. Would that work? Just negate both sides. If negative x is less than or equal to negative this expression, that also negates that. Oops. We need to subtract it from x is less than vertical rows minus this value. Pretty sure that'll do it. Sorry, greater than. Greater than. There we go. So now we have our histogram vertical. And we have our histogram horizontal. So we go down here and we'll just do 2 of these to demonstrate the difference. Okay. What would be nice to do now would be to drive this based on the terminal width instead of having those constants. And then also resample the histogram. That would be a nice thing to add, like resampling. So you provided this array of buckets and it's like, hey, you know, we only have like 200 terminal width here and you got 10,000 buckets. So every you could drop everything but every other fifth, but then you're dropping data and there could be like outliers that get dropped. So what you really want to do is consolidate the buckets together. So every 5 buckets will get consolidated into a single bucket. But that seems like a lot of work, and this is just kind of an example thing here. So what I'm going to do here is length of words in its input. I like the vertical. Lengths. And then we can also do a char frequency. So I'm just gonna comment this out, and actually we can leave that like that, fine. So we're gonna say for get char, and we say, hey, C char C, and we have to wrap this in parentheses. While it's not equal to EOF, and then we also have these counters. I'm going to say while here. There we go. So the character frequency, let's call it C frequency, is an array of 256 values. And each value is going to be a long, so it's compatible with our functions. And we need to initialize this to 0 if we can. Yeah. Okay. And then basically what we're going to say is C frequency sub C plus plus. Okay. So this is going to be C frequency. C, oh no, that's word. We'll come back to word. C frequency. And put it there too. All right. Make ASDF, ASDF, ASDF 1, 2, 3, 4. End of file. This is the 1, 2, 3, 4. I don't know what that is. We could print out the character representation of it as well. But if we just get out the ASCII table here, you could see 0 is a new line. So these are all new lines. Come on, just give me a fucking ASCII table. Decimal 0 to 10 here. Line feed, which is the new line. And then we have 1, 2, 3, 4 here. And then A, B, C, D, E, F. A, S, D, F there. So it is counting them. So what if I could just cat out horizontal? Sorry, cat out histogram. Type it into build histogram. So these are the character frequencies for that program. I don't like that. It seems like there's a new line getting printed here, which doesn't happen over here. And that is because it is too large to fit on screen or something. There we go. Okay. I'm going to put a new line there, as well as one here. Okay, so that takes care of character frequencies. Next one is word input lengths. Oh, this is fascinating. So this is going to the bucket that's the length of the word, and then putting in that bucket. So I'm going to do the same. I'll pull this up here. And I'm going to do the same 256. Actually, no, I'm going to do a 10 element one. Word W length 10. We'll do 20. And then we can do our character. Okay, so we have to do this loop together. We can't do it separately. So in here, we're going to have another thing, which is this enum state s, and it's going to be equal to we'll call this word state. Word state. Up here, we'll declare our enum word state is going to be one of a few values here, which is not word and word. Is it comma? Okay. So here we're going to say, hey, you're not a word yet. And we're going to go and say, okay, starting here, if we're not a word, and we have a character that is a word character, so if is word char of C, then and state is equal to not word, then we transition to state being equal to word, and we increment our current, or we increase our current word length. This will just be an integer. Sorry, I need to do double equals here. Come on, you can do it. I believe in you. So previously we were not a word. We got this character. It is a word character. So now we're transitioning into the word state, and we increment our we say our word length is equal to 0. And then down here we're going to say if it is a word character else if it is a word character and it is a word, then we just say word length is plus plus. Else, we know it's not a word character. I really feel like we should do like a nested if here instead of doing all these else ifs, but I'm running with it. So else if, so we now know it's not a word character. So that means that it is a other character, which should transition us. So based on our state, if state is equal to not word, or state is equal to word, I should say, then we need a transition. So state will be equal to not word, and word length is equal to 0. But, and then character count frequency we can just do down here, it's fine. We also have to record the previous word length. So if the state is word, and we're transitioning into word, not word, we need to record the word length state, or the word length in our W length array here. So this would be the previous word length, so I'm going to do it up here before I set it. Plus plus, like that. And then finally, the state is, okay, we are not a word, and it's not a word character, so we do nothing. Like that. So now we just need to define this isWord character function. So bool isWord char, and then in here, we can take our C, our char C, and say if C is equal to, we'll say not equal to, space, and C is not equal to, I'll just use the definition that they gave in the book here. Space, new line, and tab. New line, and C is not equal to tab character. Then we just return that expression. Okay. Make build histogram, and we'll say hello world, which is 5 each, and we'll say test. So we should have 1 4 and 2 5s. This is character frequency, which you don't really care about. But word input links, we got the wrong array. That was a bug on my end. What the hell is this? That can't be right. Oh, it's an old buffer. Alright, histogram C, go down here. This needs to be, instead of R, word WLEN. There we go. Hello world test. So you got hello world, which are 5, and then test is just 4. And then we already tested this guy, so we know that works. So if I run this and do like ASDF 1 2 3 1 2 3 1 2 3, why is it that these things are spaced off? I need to pipe this into less. Echo hello world How are you doing? Pipe that into that, which then gets piped into less. Here, we'll do it like that. Just full screen it. And we don't have to less it anymore. Look at that. Pretty cool. Alright, that was a fun little exercise. Alright, sorry. Let's kill that. Bring this guy back here. Kill that. Kill that. Alright, back to the book. So it is a little afternoon here. I think what I'll do is I will put a placeholder here on functions and go grab some lunch, do some cardio, and then I'll come back and we'll resume on functions. But this is a pretty fun little exercises here so far. Get status, get et al. That was a neat little program. I got to use enums. I probably could have optimized this vertical histogram. Horizontal histogram is so much easier. So this iterates over it twice, once to compute the max so that we know how to scale the values. And then this one has to compute the max, and then I guess I could have done this iteration and this iteration at the same time. Yeah. No, these are different values. This one's going over length, and then this one uses the max, so yeah, I couldn't do those. Maybe I'll go in and comment this, and then I'll take a break. Histogram. So up here, we're just going to say, same thing we set up here. I don't need that. Compute the max to scale values for output. We're going to do that again here. Then here, we're going to say initialize the output buffer. And then here, we'll say write to the output buffer. Then down here, we're going to say write buffer out. So this iteration over the array basically is two-dimensional iteration over the output array. Wait a minute. We could definitely combine some of these, because like this second length thing here, this J here, is identical to this here. So we could combine some of these, but it's not worth the trouble. It's like a minor optimization. It's a constant factor optimization. Okay, so I will take a break then, and I'll be back in a couple of hours.